So hello, my name is Witz. I'm from the company Simvantage. We're based in Graz in Austria, and today's topic is the use of computer simulation in the scale-up or characterization of bioreactors. Let's dive in. Our goal that we have is that we do the reactor scale-up, scale-down characterization process transfer based on a very deep physical understanding of the processes inside the reactor, just as you see it here in this video of a bioreactor with the bubbles, the air bubbles shown. And for that we need a validated and also scale-independent simulation software of all the physical parameters inside the reactor. And during the last 12 years we have built exactly that. So what can the simulation do? You get the fluid flow field with the flow velocity, shear stresses, and also the steering power. The steering power is often also the target of an optimization to get more sustainable operation and more economic operation. For the gas phase, we follow each gas bubble directly, therefore you get the correct holdup, the bubble size distribution, the KLA value, and also the flooding point, which we will see later. And as it is a bioreactor, we can also introduce vitreal cells, and these vitreal cells can record their lifelines, so what they feel when they float through the reactor. And with these statistics, you can then do a physical-based scale-up. We can also introduce a breakage for fungal pellets, for example, or cell death when the shear rate is too high, and then can determine the cell viability. We can also introduce particles that are affected by gravity into the simulation and then calculate suspension, settling, just the spindle speed. The particles can also dissolve, as you see it here in this picture, until they disappear. And we can also do the scale-up of microcarrier particles when we say that we have microcarriers included and then let these virtual cells impact on these microcarriers. When the oxygen is dissolved from the bubble, or like calcium chloride in this case from the particles, when it is dissolved, it is transported around the reactor with a mixing time algorithm, with a species transport algorithm where you can determine the mixing times, also the dead zone if you have a consumption of the species, and also if you use oil droplets as a nutrient, we can also tell you the droplet size distribution depending on the stir speed. And lastly, for the temperature, we have a heating or cooling jacket included, where you can directly simulate the heating fluid, but you can also simulate some submerged tube bundle heat exchanges. And let's start with the fluid simulation. We're using the lattice-Boltzmann method for the fluid simulation. What is the lattice-Boltzmann method? So the basis of all fluid movement, I think in the entire universe, are the Navier-Stokes equations, and usually they were approximated with mostly the finite volume or the finite element method. But this was very well suited for CPUs, for central processing units. But now there is the new possibility that you use the Boltzmann equation, which is the equation of statistical mechanics, to directly convert or bring these equations together and then approximate this Navier-Stokes-Boltzmann equation with the lattice-Boltzmann method. And this lattice-Boltzmann method is ideal for GPUs, for graphic cards, and as they are very fast because of gamers and Bitcoin mining, also our simulation is very fast, usually 10 times faster than the classical methods. And then we also need to simulate the turbulent field inside the reactor. And this is done with the LES method, which is like the second best method. The best method would be DNS, so direct numerical simulation, but this is currently not feasible in a full-scale reactor. And we use the subgrid model of Smagorinsky just as a detail. And then for the bubbles, we use a two-way Lagrangian model. Lagrangian means that we follow each gas bubble individually, and two-way coupled means that not only can they push the liquid, the bubble around, but also can the bubble push the liquid around. This means when you have bubble column, then the rising bubbles take the liquid with them, and then you get this rotating motion of the liquid with this two-way coupled Lagrangian model. To know how the bubbles move around, we solve the Newton's equations of motion. And this means we sum up all the forces that are acting on the bubbles, and then we get the resulting force, and with that we know where the bubble is at the beginning and the end of the time step. And then in very large reactors, the number of bubbles is way too high. Therefore, we use the puzzle approach to group similar bubbles together and just transport one representative bubble. For the breakup and coalescence, we use the coalescence model of Sommerfeld, where you measure how this contact time is, and this time this little film between the bubbles that are in contact takes to rupture, and if this film rupture time is longer, then the bubbles just separate again. If the film rupture time is shorter, then a big bubble is formed. But they cannot only get larger, they also get smaller, and this is done with a breakup model, and this breakup model considers the main source of the breakup is turbulent eddies, and these eddies in the same size range of the bubbles can rip the bubbles apart. Now, for measuring the power number, you have two possibilities. The first one is a torque method, where you have little fields on your stirrer and measure all the forces acting on this square field on the stirrer, and then you multiply it with the distance to the axis, and if you do that for all these fields covering the whole stirrer, then you know the total torque. But you can also say that the energy that the stirrer brings into the liquid has to be distributed and dissipated somehow, and therefore you're measuring and summing up all the energy dissipation in the whole reactor, and therefore know how much power you need to put in. And if you compare that and calculate the power number, you see that you get a very good agreement between these two methods, and also the correct power number for this Russian type stirrer. And this agrees not only in the turbulent regime, but also in the transitional and laminar regime. Now, if you want to know if your stirrer is efficiently distributing your bubbles, then you want to know if the stirrer is flooded or not. If the stirrer is flooded, then it cannot separate or distribute the bubbles throughout the whole diameter of the reactor, and therefore the bubbles flow to the next stirrer or to the headspace of the reactor. If the stirrer is not flooded, then it can directly distribute the bubbles through the whole diameter and has a normal operation. So how to simulate that? You place a virtual cylinder around the stirrer, and if you have a normal operation, then the bubbles flow outward and take the liquid with them, and then you have a positive flow rate through the virtual cylinder. And if the stirrer is flooded, then the bubbles go to the next stirrer or to the top of the reactor, and then you get this rotating motion of the liquid, and therefore you get a negative flow rate through this virtual cylinder, which you can see down here. Here is the steering rate, and if the steering rate is too low, then the stirrer is flooded, and if it gets over a transitional point, then it can distribute the bubble again and it's not flooded anymore. And you can now determine this on the computer and also compare it with experimental values from Ramos Kerken, and you see you have a very good agreement between the simulated value and the literature value. Now, if you think about the surface of the reactor, oftentimes you have a vortex, which is sometimes responsible for foaming, but it gives you also an increased surface area, and this increased surface area can be used for headspace gassing, and therefore you want also to be able to simulate that. And for that we use a volume of fluid model where we distribute this interface between the gas and the liquid into gas nodes, liquid nodes and interface nodes. Don't mind all the formulas, but what the problem is that we use such density distribution functions, and if we have an interface nodes, these density distribution functions coming from the gas phase are missing, and therefore we have to calculate them, and we calculate them with the headspace pressure, or in case of bubbles with the initial volume versus the current bubble volume and their initial pressure, and also the curvature of the interface, because an increased or a sharper curvature increases the pressure on this interface because of the surface tension. And you can also compare that to experiments, and we did that together with the Hochschule Niederrhein in Germany, where we compared experimental results and simulated results. And when you look at the graphs, you see that you have a very good agreement either in the volume of the simulated and the experimental vortices, and also the depth, how low does it go. You have a very good agreement in an unbaffled case, and also in a baffled case here, cylindrical baffles were used, and you see here that you have also a very good agreement between those two methods. And as I said, the vortex simulation can be used to calculate the mass transfer of the oxygen into the liquid, and you see here in this picture the oxygen distribution that is purely coming from the headspace. And if you think about, for example, very small reactors like the Storis Ember 250, the aeration through the headspace can make a difference of 50%. So if you don't include the headspace aeration, you get a 50% error in your KLA calculation. Now I would like to show you an application of this software in a mixing study. And the idea behind that is that you have an approved manufacturing process and a necessary change. And then what you usually do is a series of expensive and time-consuming experiments. And then hand that data to the FDA and the EMA for approval. What would be better is that you do, instead of a lot of experiments, fast and cheap virtual experiments, and then only one real experiment if necessary, and then hand the virtual experimental data and the real experimental data as a validation to EMA and FDA, and then you save a lot of time and experimental effort. And now you may ask, okay, are the regulatory authorities willing to accept these simulations? And the answer is yes, they're very much open to this, but you have to do validation cases. And the advantage now with our software is that we have first principle algorithms in this in this software, and therefore we are allowed to do the validation cases at a certain point, let's say 100 RPM, and do the real case at 150 RPM. Because the physics doesn't change between 100 and 150 RPM, you can say that your validation case is also valid for your application case. This would not be possible if you use data-driven methods. And I would like to draw your attention to this FDA guidance. It is for medical device submissions, but the assessment of the simulation algorithms, which is described here, can be easily transferred also to manufacturing. And this relies on the SME and V40 standard, also for medical devices, but again, this can be easily transferred to manufacturing. And now one of these validation cases I would like to show you, which can then be used in the regulatory submission. Here is the experimental data of Xi et al. On the x-axis, with our simulated data on the y-axis, and ideally all these points should be on the 45-degree line, because this would mean that the 95% mixing time of 10 would in the experiment would then agree with the 95% mixing time of 10 in the simulated experiment or in the simulation, and this would have a perfect agreement. And the farther away these points are from the 45-degree line, the higher the error is, and you see that we have a very good agreement for the 95% mixing time, and also for the KLA. For the KLA, the error is slightly higher, but everyone who has measured KLA experimentally knows there is a certain error bar associated with these experimental values, because the KLA is very hard to measure. And we did also validation not only in the small scale, but also in the industrial scale with a 160 cubic meter reactor. And this reactor had two conductivity probes, and a salt was injected at the top and then was homogenized by the 4 impellers. And we did a digital copy of this reactor in our software, placed 2 virtual probes at the position and injected a substance at the top and let it homogenize. And then you can compare the measurements of the virtual sensor in green with the black experimental measurements, and you see that you have a very good agreement for both sensor positions. And then this was not the end of this project. The engineers then played around and changed the stirrer configuration in this reactor, and they chose then to change every second stirrer with a pitch blade turbine, so with an axial stirrer, and this change was also then done in the real reactor. So the stirrer configuration was changed in the real reactor, and they had a 20% reduction of energy demand while achieving a 30% faster mixing, saving them approximately 350,000 euro per reactor per year. And this is also published in a paper of 2022. Another practical example is the temperature distribution. And the problem with the temperature distribution in simulations is that if you only simulate the reactor, you don't know the heat transfer coefficients from your heating jacket into the reactor, and also from the reactor wall into the fermentation broth, for example. And therefore, you also have to know the heating and cooling power of your jacket, and oftentimes this is not known because you don't have enough sensors. What we did is that we include also the jacket into the simulation, and therefore you only need to know the temperature and the flow rate of your heating or cooling medium that goes into the jacket, and everything else is calculated throughout the simulation. And it looks like that. You see the hot liquid flowing into the jacket, and then inside the reactor it is slowly warming up. And just as an example how such an algorithm works, you have the bulk temperature in the jacket and in the reactor, and then heat is the heat transfer coefficients H1 and H2 are calculated for both sides depending on the liquid flow field, and then the energy transfer is calculated from the jacket into the reactor content. And you can compare this also with experimental value and see that you have a very good agreement in the heating up of a reactor. And this can also be used for troubleshooting, and we had one case where there was an unexplainable cooling inside the reactor, and we could show that this cooling was from the air bubbles from the compressed air and is too cold, and then the liquid cools because of this cold air, and this was also recognized, of course, by temperature sensors and led to a decrease in productivity. And we could show with the simulation the reason for that unexplainable cooling and helped in the troubleshooting of this case. Now, as I said earlier, we also can simulate particles. And these particles, as you can see here, flow around the reactor and then dissolve partly, and this dissolution can then be shown in diagrams for different diameters of particles. The one is the experimental value and the other one is the simulated value. Again, you have a very good agreement, and this dissolution can also then go until the particles are completely dissolved, and this dissolved substance is then transported around the reactor. Another use case how you can use this software is the control of continuous bioprocesses, and for that we are working together also with a central data management and also hybrid process model. The central data management is done by our partner Cubicon, and the hybrid models are done by a company Novasign. And if you combine all these three tools, that you can directly get like the steering rate in our models and give back the KLA and shear rate, current shear rate, or if you give our values to the hybrid process model, then you can achieve a much better knowledge about your process. And this then leads to an optimization of your process with less experiments. You can get a better scale up with better knowledge about your process conditions, and you can also have an instant access to all relevant processes and quality data with the central data management. You can also get a model-based decision tool for the operators, that the operators know in advance what their change they want to make in the reactor's operation, what this would mean for the yield, for example, or what this means for the shear rate inside the reactor. And all of that leads to more consistent batches and fewer batch failures. And we could realize that as a use case supported by the Austrian Research Promotion Agency in the project ICANTE, which was the largest Austrian life science project by the FFG. And here we built a whole continuous biological production line, starting with the raw material, going over two reactors, and then a recovery and downstreaming purification with a MCC from Tosu, and then we reached a product which was a protein A, and this protein A was our model protein. All the data came together at our partner Cubicon, which then told us all the information we need for the bioreactors, and then we gave our results back to Cubicon to display to the operators, and to Novasign to improve their hybrid models and to inform their hybrid models, which in turn they gave back their data also to Kibikon. And this then leads to a better prediction of the biomass and the product. You see here in blue the biomass predicted and measured. The points are the measured values, the lines are the predicted values. And you see here that the dilution and the temperature was changed, and the model could predict that very well. Last use case I would like to show you is the model-based scale-up. So for the model-based scale-up, I would like to give you a simple example to scale up from the Eppendorf DASKIP to the Cytiva XDR10. This is only a very small scale-up. You can also do larger steps to scale up to a 100-liter reactor, for example. And for the scale-up, you can have various different parameters and also parameter combination, like the concentration of oxygen at the cell's location, the KLa value of the reactor, the shear rate distribution, the mixing time, nutrient concentration, whatever you can imagine, you can use as a scale-up criteria. For this example, I would like to use the shear rate, but as I said, the workflow is the same if you use other parameters or combination of parameters. And now we introduce the cells into our virtual reactor, and these are massless particles that flow with the flow field, and then you can record the lifelines. And the lifelines are what the cells feel, the cell's microclimate, and if we can keep this cell's microclimate around the cells constant in the scale-up, then we achieve a perfect scale-up because the cells only care about their very small environment around their location. Now for the DASKIP, we do exactly that. We measure the shear rate distribution in the simulation software for Newtonian viscosity water or non-Newtonian viscosity, a shear thinning liquid. And we do that because oftentimes you start with a Newtonian viscosity with a low cell count, and then if you increase the cell count, you come to a non-Newtonian viscosity, which can then lead to a different shear rate distribution. And here you see the shear rate distribution inside the reactor. And what we now know is the average shear rate for both cases and the power per volume value, which is around 40 for both cases. The power per volume is often used as a scale-up criteria if you want to scale up with the same shear rate. And we want to test that if that is true. And now what we did is to do several simulations with the XDR10, and then this XDR10 simulations were evaluated and post-processed, and then the steering rate was changed until a match between the shear rate distributions was achieved. The first one is the Newtonian viscosity, where we match the steer speed to 110 RPM, and then the non-Newtonian viscosity, which we matched at 160 RPM. And this the different speed is because of the different shear rate distribution throughout the reactor. And now let's come to the results. We again have an average shear rate distribution, but now for the power per volume value, you see that you have a good agreement for the Newtonian case. So this means the scale-up would have worked for this case, but in the case of non-Newtonian viscosity, the power per volume value is vastly different. This means if you have scale-up here with a constant power per volume, it would lead you to a wrong or a different shear rate distribution. With the CFD, you get always the correct distribution of shear points. And that then leads you to this in silico scale-up process, where you have your SUS reactor with the operating parameters, and with a rapid response model you can convert these operating parameters to the cell's microclimate, and then you can use an optimizer which finds you the same cell microclimate in your target reactor, also with a rapid response model, and then you get the operating parameters of your target reactor. Now, proof of concept for a 2 liter to a 100 liter vessel. We saw that for the chosen stirrer speed and gas flow rate and broth rate for the 2 liter vessel, we get a certain KLA and mixing time. And this KLA and mixing time are now also the targets for our 100 liter vessel. And the shear rate, of course, is a distribution. And now you see the optimizer. If we are at the first iteration, it finds a certain stirrer speed and gas flow rate, basically a gas. But you see that the KLA value and the mixing time do not match, and also the distribution, the reference is the blue line, and the red line is our target. And you see that these two don't match, but after the 22nd iteration of our optimizer, you see that we have a very good agreement between KLA and mixing time, and also the shear rate distribution matches. Therefore, you know the steering speed and the gas flow rate that give you a very good agreement between those two reactor processes. And these two operating parameters are now the first values. They will not be perfect, but they are the first values for your technical batches, and you arrive at a very good process much faster. And we also converted that in a cloud-based software, so you can do this also in the cloud. You have your source reactor on the left, where you can choose your reactor vessel, then set the operating parameters in your source reactor below that. And then you have a target reactor. You can set again your target reactor where you want to transfer the process to, and also then you can change the operating windows for the target broth weight and stirrer speed, again what the reactor can do. And then you can also enable that weights for certain parameters. If you do not enable that, then the optimizer tries to optimize every variable like shear rate, KLA, mixing time. But you can also set that the mixing time is very important for you. Then you click one button, so it's a one-click solution, and then it calculates and does the iterations in the background. And after that, you will present it with the operating conditions, which most closely match your reactor, which most closely match the source reactor's configuration. So for the source reactor, you have these operating parameters, which leads to these scaling parameters, the best match in your target reactor, and the suggested operational parameters for the target reactor, which means you go directly from the operating parameters from your source reactor to the operating parameters to your target reactor, and you can also look at the overlap of your shear rate distribution, for example, here. And you can also get a PDF report about that, of course. And that's all I wanted to tell you today. My name is Christian Witz. You have my contact details here. If you ever need more insight into your reactor, please contact me.